Good morning, students. Myself, Vijay Shankar from BC Department, Chevron Engineering College. Today, we are going to discuss about the distortionless transmission through the system. In previous class, we've seen some examples of stable, unstable system, causal and non-causal system. And before that previous class, we discussed about the examples in the linear time invariant system. Linear system, non-linear, and time variant and time invariant system. Now we go for the another topic, that is a distortionless transmission through system. So in this distortionless transmission through the system, it means the output signal is an exactly replica of the input signal. Without any distortion, whatever the signal we transmitted from the transmitter side and receiver at the receiver side without having any noise or the distortion occurs. Means exactly the replica. Whatever we send from the transmitter, that is the input signal, exactly replica of the input signal. Input, it passes through the system, it get the output. The difference between the input and output of such system is that first 2 points we have. Amplitude of the output signal may increase or decrease by some factor of with respect to the input. Amplitude of the output signal may increase or decrease by some factor of with respect to the input. Let us consider here the K is an amplitude. So the output Y of T is equal to. That signal can either increase or decrease the amplitude. K is equal to. And the output signal may be delayed in the time with respect to the input signal because of system delay. Due to the system delay, the output is also delayed here, not for the delay of the input signal here. So the input, the delay, let us take here the x of t minus t naught. Because the output will get the delay due to the system delay, the y of t is equal to. Y of t is equal to k into x of t minus t naught. The constant represents the change in the amplitude, and the t naught is a time delay in transmission of the signal through the system. Got it, my students? Now we can apply the Fourier. Y of f is equal to the Fourier transformation of the time delay function e power minus j 2 pi f into t naught into x of f. Okay, my dear, this is a y of f is equal to k into x of f e power minus j 2 pi f into t naught. Only the difference between the input and output of such systems is its amplitude either is increasing or decreasing with a factor of the k here, and the output may be delayed in the time with respect to the input signal because of the system delay, the x of t minus t naught. After applying the Fourier transformation on both sides, y of f is equal to some k into the x of f e power minus j 2 pi f into t naught. Okay. Then we got the y of f is equal to x of f into k, the exponential factor e power minus j 2 pi f into t naught. Now the system function, the h of f is equal to the transfer function output by the input in the frequency, the y of f by the x of f is equal to k into e power minus j 2 pi f into t naught. Okay. The phase shift here, let us assume that is a theta of f is equal to e power minus z theta. Let us take this a theta value. The theta of f is a 2 pi f minus is also there, 2 pi f into the t naught. Okay. And the magnitude is a k1. The h of f, the phase shift is a linearly proportional to the frequency, and its amplitude spectrum is a k, is a constant. and here it is a passes to the origin. When f is equal to 0, the value is 0. When the f value is the negative values, we get the positive here and goes to the negative. Is time domain signal x of t is equal to cos 2 pi f into t. Delayed when it passes to the theta of f, the theta of the 2 pi f into t naught, which is proportional to the frequency f, f. Distortions. One is amplitude distortion and the phase distortion. The gain and the phase distortion. The distortion occurs when the phase of h of omega is not linearly changing with the time. Previously, we got the expression is a linearly changing function, which is not, and the different frequencies are selected to and e power minus j 2 pi f into t naught, which is distortion for that one. If it is not the linear, then we get the phase distortion. If the amplitude is the amplitude distortion, nothing but a constant. If it is a variable, you get the distortion occurs in the amplitude. This distortion occurs when the magnitude is band of interest and the frequency components present in the input signal are transmitted with a different gain and attenuation. Okay. Now go for with the signal lower cutoff frequency and 3 dB frequency. It is a high frequency, it is a 1, and at the 3 dB frequency, you will take the point not 1. Omega 2 is a high frequency and omega 1 is a low frequency. Omega 2 minus omega 1 is the band of frequency that contains most of the signal energy is called a band of signal denoted by the FM. It is a range of significant signal frequency. Observing the waveform x of t as a significant frequencies from omega 2 to the omega 1 or omega 1 to the omega 2. The bandwidth of this unit signal is omega 2 minus omega 1. Lower cutoff frequency. All the physically obtained signal have limited bandwidth. Okay, we know with nothing but signal. 1 by under root of 2 is nothing but 0.707 minus 0.707. This is exactly the 3dB frequency. The bandwidth of the system is defined as the range of frequencies for which the magnitude remains within the 1 by root 2 times of the midband value. Actually, for the low frequency, slowly it is increases. At the mid frequency, it is 1 by root 2 or 0.707. Let with the omega 1 and the omega 2 here, the band of frequency within the 1 by root 2 times of the midband value. For distortionless transmission, the system must have the infinite bandwidth, but physical system are limited to the finite bandwidth. The finite bandwidth is omega 2 minus omega 1. And so a system with finite bandwidth can provide the distortionless transmission for a bandwidth signal if magnitude of h of omega remains constant over a bandwidth of the signal. And the range of frequencies for which the magnitude of h of j omega of the system remains within the 1 by root 2 of its maximum value. Got it, madam? These are the definitions of the amplitude distortion, phase distortion, signal bandwidth, and the system bandwidth. Understood? You can take the range of the system bandwidth for the and next. We know the causal signal. Causal signal means having only the positive relaxes, the negative relaxes totally the zero. The system is said to be causal if h of t is equal to 0, if t is less than the 0. There is no any term in the negative relaxes. Okay, total the value is 0, then we can say that is a causal system. If the input is a 0 for t less than the t naught, then the output is also 0 for t less than the t naught. Any system which does not obey the above rule is non-causal system. If does not obey the above rule means non-causal system, which obeys the rule means causal system. Means let us take here the unit step function is a causal, and if it is shifted towards the left side, it is not a non-causal system because it depends upon the feature also, feature inputs. Got it? Causal system means it depends upon the present and the past inputs only. It does not depends upon the feature inputs. So the input is not the value. You can take the get to bring that it is the input feature inputs are the 0. You can take the h of t value is a 0. If the two inputs of the two input to a causal system are equal up to the some time t naught, then the corresponding output must be equal to up to the time instant. Okay, so why I am saying here the x of n or the x of t, let us take this x of t. In the convolution function, when you can expand the n is equal to minus infinite to infinite, x of let us take it is a k value, x of n minus k into h of k. Expand this value from so on, x of n minus of minus 1, nothing but the plus h of minus 1 plus x of n h of 0, k is equal to, I am substituting the minus 1 here, and the next is a 0, and the plus 1 x of n minus 1 and h of 1. See the combination of the input signal, there is a impulse response also. When we can say it is a causal system means it depends upon the present and the past inputs. It does not depend upon the future inputs. To bring this, the value is a 0, how to take the equation that h of n is equal to 0 for n less than the 0. H of n is equal to 0 for n less than the 0 in the discrete function, or the h of t is equal to 0 for n less than, not n, sorry, t less than the 0. Okay. Next is the Wiener criterion. What is a Wiener criterion? And what is the relation between the rise time and the bandwidth? This gives a condition of causality in frequency domain. Condition of for causality in frequency domain, or in other words, the frequency domain equivalent of causal system h of omega. Previously, we take here the h of t, the causal system. Wiener criterion means it gives a condition for the causality in frequency domain, that is h of omega. H of t, we know that h of t is less than is equal to 0 for t less than 0. In the Wiener criterion, the causality taken the frequency domain for the h of omega. What is that condition here? Consider the system with the transfer function h of omega. The necessary and sufficient condition for h of omega to the transfer function of causal is integral minus infinite to infinite ln of h of omega, magnitude of h of omega by 1 plus omega square into d omega is less than the infinite. Nothing but this total integral value you have to get as a finite value only. Or otherwise, provide that this h of omega is a squared integral minus infinite to infinite squared magnitude of h of j omega d omega is less than the infinite. This is a Wiener criterion of a condition 2 is not satisfied, then the condition is 1 is neither necessary nor sufficient. If this is not satisfied, but it is necessary, but it's not the sufficient condition. Okay. This is a causality in frequency domain. We can call it as a Wiener criterion. And causality we already know in the time domain, h of t is equal to 0 for t is less than the 0. What is my difference? And we can derive the physically realizability for this. A system is said to be physically realizable if it obeys the causal condition h of t is equal to 0 for t is less than 0. Let us take the example h of omega is equal to 1 plus j omega. H of t is e power minus t mu of t. H of t is equal to e power minus t mu of t. See, the mu of t is multiplied means only it is from 0 to infinite. The less than the t, the variable is a t. For less than the t is less than the 0, the value becomes 0. So h of t is equal to 0 for t is less than the 0. For the function h of omega is equal to 1 plus j omega. So the above equation less than the infinite. Okay. Or otherwise, you can take the squared magnitude of h of omega d omega is less than the infinite. You can prove that value is a finite value, then it satisfies the condition. Wiener criterion. Okay. The frequency domain statement can be interpreted as h of omega, a physically realizable system, maybe 0 for some discrete frequency, but it can never be the 0 for the finite band of frequency. H of omega for a realizable system cannot decay faster than the function at the exponential order. The system with transfer function e power minus omega is realizable, whereas the e power minus omega square is not, as it is a decay faster. Understood? Then you can see the relation between the rise time and the bandwidth. Relation between the rise time and the bandwidth. The TR is equal to. Rise time means time taken to reach 100%. Delay time means time taken to reach the 50%. Peak time means the time taken to reach the peak value. Understood, my students? Is the rise time and the relation between of the rise time and the bandwidth. You know, the bandwidth is upper cutoff frequency minus lower cutoff frequencies. Let us take here to derive this expression. It is a very important, my students. Listen carefully. The previously all it is a definitions only. Wiener criterion and system bandwidth, signal bandwidth, and phase distortion and amplitude distortion. The relation between of the rise term and the bandwidth is a derivation part, and it is a very important examination point of view also. If a unit step function mu of t is applied to the ideal low pass filter, the step function is applied to the ideal low pass filter. The output with will show a gradual rise instead of a sharp rise of the input function. Giving that the input it passes to the low pass filter and will give the response is a linear response R of t, as R of t is equal to t for the t is greater than or equal to 0. So the transfer function of the ideal low pass filter is h of omega is equal to magnitude of h of omega into e power j theta of omega, where h of omega is a rectangular pulse with a magnitude of k. You can take a minus b less than or equal to f less than or equal to b, as we already know the rectangular function in between of minus b hertz to the b hertz, or in terms of the omega n to the omega band limited to the function, where omega m is equal to 2 pi into f. What is the f here? The beta is omega m is equal to, we know the 2 pi f. What is the f here? Is nothing but the frequency in hertz. The 2 pi, sorry, b. Got it, my students? And the theta of omega is equal to minus 2 pi f into t naught. We already know the function in there. That is omega into t naught. The cos 2 pi f into t, and it is a delayed version, the 2 pi f into t naught. This total cos function having the theta of f or the pi of f is a minus 2 pi f into t naught. That's 2 pi f is a omega minus omega naught, omega into t naught. Okay. The Fourier transformation of the unit step function, the mu of t is the Fourier transformation of the step function, the mu of omega is equal to, because we are applying the step function here to the low pass filter, passing through the low pass filter. Fourier transformation of mu of t is a pi into delta of omega plus 1 by 0 pi into delta of omega plus 1 by j omega. The Fourier transformation of the response. So what is the Fourier transform? The output function R of omega, and the input is a step function, and here the system is h of t. Let us take a system and the system R of t is equal to mu of t with the convolution of h of t, and apply the Fourier transformation on both sides. It becomes of R of omega is equal to mu of t, nothing but mu of omega, into the convolution becomes product in the frequency h of omega. So what is the mu of omega? Pi into delta of omega plus 1 by j omega into the whole multiplied with the h of omega. Got it, my students? That we can note here. R of omega is equal to pi into delta of omega plus 1 by j omega into h of omega. Multiply this h of omega for the two terms. pi into delta of omega into h of omega, 1 by 0 omega into h of omega. Okay. And you can take the step function as an input function. A system is a low pass filter. Inside that is a h of t, the impulse response. To get the response is a ramp function, r of t. The frequency response of the is r of omega is equal to pi into delta of omega h of omega plus 1 by 0 omega into h of omega. Next, the delta of omega. So here in this function, the delta of omega exists only for omega is equal to 0, because the impulse function get only at one value only, at omega is equal to 0. Got it, my dear students? So at omega is equal to 0, they exist only at the for omega is equal to 0, and h of omega at omega is equal to 0, the value is 1. Okay, then it becomes of r of omega is equal to pi into delta of omega plus h of 1 by 0 omega into h of omega. So I take here the delta of omega, the value is 1. At omega is equal to 0, the h of omega, the value is also 0. So combination of delta of omega and h of omega. By taking the inverse Fourier transformation of the above function, r of omega is r of t, and inverse Fourier transformation of r of omega is pi into delta of omega plus 1 by j omega into h of omega. I substitute here the h of omega is equal to 0. At omega is equal to 0. Got it, my dear friends, in the first equation, first term. So inverse Fourier transformation, pi into delta of omega plus 1 by j omega into h of omega, if I am written as h of omega is equal to, when it having the magnitude and the phase, let that magnitude is considered as a z omega and e power minus omega into t naught as a phase value. Substitute that h of omega as z omega into e power minus j omega into t naught. So the inverse Fourier transformation pi into delta of omega is a 1 by 2. How we got this? The Fourier transformation of 1. Fourier transformation of 1 is 2 pi into delta of omega. You know, in the Fourier transformation we discussed this one. And the Fourier transformation of 1 by 2, the constant, the 2 will get, then it becomes of pi into delta of omega. So it is the frequency for inverse Fourier transformation is 1 by 2. So the pi of delta of omega, the inverse Fourier transformation we are applying here. So first term is becomes of 1 by 2, and the second term what we have here, the inverse Fourier transformation of 1 by j omega into z omega e power minus j omega into t naught. Okay. Let us directly apply the inverse Fourier transformation using the formula 1 by 2 pi into, to get it is a g of omega is there, nothing but is h of omega, the 1 by 2 pi into minus infinite to infinite, 1 by j omega g of omega, the total function is e power minus j omega t naught whole multiplied with the positive exponential j omega t into d omega. Okay, and this j omega is varies from here minus omega to the omega. We already told that a rectangle function in between of minus b to the b, or it is a minus omega m to the value is a 1. So that z of omega, we can write it as a 1 by 2 pi in the range of minus omega m to the omega m, 1 by j omega into, let it is representing the g of omega is equal to 1. And here the exponentials, both the exponential base is the same. Let us take the j as a common. Minus j, not the minus j, it is a plus j, you can take as a common. Omega is also the common term, j omega into t minus t naught into d omega. Got it, my students? So 1 by 2, and now the integral is minus omega m to the omega m e power j omega into t minus t naught whole divided by j omega into d omega. Got it, my students? We know the e power plus j omega, you can write it as a cos, and in terms of the sine, the e power jx is equal to cos x plus j sin x, or e power minus jx is equal to cos x minus j sin x. You know, this is a function equation in the trigonometric equations. You can add these two functions. Cos x is e power plus jx minus, not the minus, plus e power minus jx by the 2, the Euler's rule. You can add these two functions, you'll get 2 cos x is equal. So cos x is equal to this function. So the e power jx, you can write in terms of the cos at the sine, 1 by 2 into the integral minus omega m to the omega m. Write the enumerator function as a cos omega x term is omega into t minus t naught plus j into sine omega t minus t naught whole divided by j omega into d omega. So this is the integral with respect to the omega. The two integrals we get. We know in the full cycle, the cos function is always the 0. So 0 for its odd term. Okay, my dear students, the cos function is always a 0 only, or it's a 0 for its odd function. Understood? Then the second term, what we have here, the 1 by the omega. This is an even function. Okay. Now, the R of t is equal to 1 by 2, the plus 1 by 2 pi into, when it is an integral, is an even function, means you can multiply the 2 and change the limitations as minus omega m to the omega m as 0 to omega m. Got it, my dear students? If it is an even function and the odd function, if odd function means a 0 in the full cycle, and here the even function means multiplying with the 2 and changes the limitations as a 0 to omega m. 2 into. So sine omega t minus t naught by omega into d omega, and 2 to get cancelled here. 1 by 2. This is for the inverse Fourier transformation of pi delta of omega plus 1 by pi. After cancelling the 2, integral 0 to omega m sine omega pi omega into t minus t naught by omega into d omega. Sine by function, the integral is a sinc function. Sinc of omega by the t minus t naught the omega m to the 0. Okay, the sine integral becomes omega m to the 0. The upper limit is omega m and the lower limit is 0. So the rise time is given as TR is equal to 2 pi by the omega m, that is 1 by z b. The omega m is nothing but the range is from the minus b to the b. So that is a minus omega m to the omega m. Okay. So the rise time is given, the TR is equal to 2 pi by the omega m. And that omega m you can written as a b, 2 pi by the b, the cutoff frequency of the low pass filter. The TR is equal to 1 by TR is equal to omega m by the pi by the pi. The frequency of the low pass filter. The TR is equal to the relation between of the rise time and the bandwidth. Now it is omega m. Actually, you can write it as a 2 pi. Why it is a 2? Omega m is equal to, without confusion, 2 pi by b. They get cancelled. The TR is equal to 1 by b. The TR is equal to 1 by 2 pi into b. It get cancelled. The rise time is equal to 1 pi. What it matters? Inversely proportional to the bandwidth and to the rise time. Rise time is inversely proportional to the bandwidth. Our bandwidth is inversely proportional to the time. TR is equal. It's nothing but the frequency one. The omega m is a frequency. The time is always inversely proportional to the frequency matters. Or frequency is inversely proportional to the time one. Got it? See the diagram here. Why I am writing that? It is 50% reaches the delay time, 100% it reaches the rise time. So in this diagram, the 50% is relays nothing but the TD. TD is a delay time, and 100% nothing but the 1 is a rise time. At this stage, you get the omega m by pi, the waveform. Omega m pi, that is a TR is equal to, we got omega m by the pi. Okay. The omega is y of t is equal to x1 and x2.